Hello, and welcome to our 5th lecture in aerodynamics. Last time, we covered non-dimensionalization, our strategy for considering dimensional quantities relative to important flow parameters. Also, we covered similarity. When scaling a problem, there are non-dimensional numbers you need to keep constant in order to ensure your two scales are comparable. Today, we will be going over conservation laws. You likely have seen these in fluid mechanics, and since air is a fluid, there also are governing equations in aerodynamics. We will take a physical approach to understanding the conservation of mass, momentum, and energy. So let's jump in. The conservation laws of aerodynamics are the governing equations that describe in detail fluid flow behavior. These are the same laws as in fluid mechanics, though some of our assumptions or lack of assumptions are common due to our working specifically with air. In order to predict flow behavior and the forces a flow imparts on an object, we need to apply rules to the flow mechanics. The first of these rules is conservation of mass, which simply states that if more gas goes in than out, then the mass of your container must change. Second, we have conservation of momentum, which is famously F equals ma, our favorite of Newton's equations. Last and least likely to be used is the conservation of energy. If you have a container of fluid that you apply work to, or heat, that means the internal energy of that fluid must change. In this video, we won't derive these equations. Derivations of the equations are easy to find online and in books in all forms, whether they're derived in differential form or integral form. Here, we're going to take a physical perspective. It's my goal at the end of the video that you have a physical grasp over what each term in each equation is. First up, we have the conservation of mass. The official principle here is that mass cannot be created or destroyed. Consider a container of fluid. This law states that if more goes in than comes out, the mass of that container must change. Here we think in terms of mass flow rate instead of mass itself, which is easier for fluids analysis. When taking a fluid's perspective, the equations change a bit. Here and throughout the rest of the video, we are presenting the equations from an Eulerian point of view, meaning we fixed an observation window in space and we watch the fluid as it passes through. Here's how the conservation of mass looks for a compressible fluid. There are 3 spatial gradients, summed and set equal to the time rate of change of density. Below, let's sketch what each term physically represents. Consider a cube of fluid. This is our observation window in 3-dimensional space. This cube has fluid in it, so it has a mass. The first term represents how much different the flow rate is coming in than leaving in the x direction. If fluid is leaving faster than it's coming in, then this term is positive. Similarly, the second and third terms represent the fluid passing through the y and z directions. Say we have only flow in the x direction. If fluid leaves our cube faster than it comes in, then our cube starts losing fluid, and that's when the right-hand side comes in. This represents a negative change in density over time. Physically speaking, our cube is changing weight. Now, when the cube has the capability to change weight, that means that more fluid is being compressed into the cube or expanded out. This means we're dealing with a compressible fluid. However, many fluids are not compressible, and we make an assumption called the incompressible assumption. Mathematically, this means that the density terms are constant, so any derivative of just the density is 0. And if the density is in a derivative, it can pop out of it, leaving behind whatever was left. So, if we apply these new assumptions to the above equation, we get the conservation of mass for an incompressible fluid, and it's just the balance of 3 spatial gradients of velocity. The right-hand side is 0 because we physically cannot change how much our fluid weighs. Incompressible is a great assumption for liquids, and also can be made for slow-moving gases. Although sonic speeds happen near Mach 1, to be truly incompressible you want to be safely under Mach 0.3. Now we move on to the conservation of momentum. The physical principle here was first stated by Isaac Newton and says that an object's change in momentum must be due to a force. This is quite famously referred to as F equals ma. More generally, however, we would write that this F equals the time rate of change in momentum, mass times velocity. For a fluid, it really is this simple. You have external forces that act on a fluid, internal forces due to friction, and that is set equal to the fluid's change in momentum. However, they don't look nearly this simple when you write them out. Each direction in space has its own conservation equation, so in 3 dimensions we have 3 equations. Let's start by taking a second and writing out the skeleton for the equations. Here, what you will notice is I am first writing a lot of terms in red, as we did above. However, I'm intentionally leaving spaces where I will add variables after. I'm going to copy and paste the skeleton for all 3 directions because it's the same. Now, I'm going to start filling in the variables that are unique to each direction, and they'll be in white. White variables are what's different between the 3 equations, and red variables are the same. For x, you see all u's, which is the x velocity, or x's. For y, you see v's and y's. And for z, you see w's and z's. By now, you're likely familiar with all the variables. Remember, mu is the viscosity of the fluid, and here I represent the general body accelerations as the letter A, with the subscript denoting the direction. This is the generalized form of the conservation of momentum equations, and is famously referred to as the Navier-Stokes equations. Note here we make use of the material derivative because of our Eulerian point of view. This material derivative has the time gradient in it as well as convective spatial gradients to indicate acceleration. As before, let's consider each term physically. The first term, the material derivative, represents the primary change in the flow momentum. This includes traditional acceleration, or the momentum changing in time, and the convective acceleration, where the velocity is steady in one location but changing throughout space. The reason for needing both of these is because of our fixed observation window. Next, we have the change in momentum in our observation window due to stuff either expanding out or compressing in. If fluid expands out, that means it is also pushing some of the momentum that it had before out of it. This term is directly associated with compressibility, which is why we see that specific set of velocity gradients summed together in the parentheses. And that covers everything on the left-hand side of the equation, all of the changes in the flow momentum, or the ma. The right-hand side is the F. It's the collection of possible ways to force the fluid in our observation window. First up, we have the pressure gradient. As you know, pressure comes from molecules bouncing off one another in a certain space. And if there are more bouncing on one side than the other, you get a gradient. And this gradient means there is a force that can drive fluid motion. Next, we have the traditional forces due to viscosity, or the flow friction. This again comes from molecules bouncing around, but this time they're jumping from one streamline to the other and bringing with it a change in flow speed. This results in an internal fluid stress that changes the local fluid momentum. Thus, we get a force. Next up, we have a special viscous force due to the expansion or compression of our volume. If you consider 2 particles in a partially inflated balloon, one in the center and one near the edge. When you start to blow up that balloon, the particle at the edge will move away from the center, so it has a certain velocity. The particle in the center, however, stays put, so no velocity. Thus, the expansion or compression of a fluid in our window gives us velocity gradients, and anywhere there are velocity gradients, there are potential viscous forces due to those pesky molecules bouncing around. And last, we have body forces. These are not forces directly acting onto our cube of fluid itself. They're magically attracting or repelling the fluid. The most common to see here is gravity, but You can also find magnetic forces in special types of fluids, or Coriolis forces due to a rotating reference frame. The list goes on. Now, this set of equations appears intimidating, and that's because they are. They're so difficult to solve that they represent one of the millennium problems in mathematics. Luckily, we almost never see them in the full form, partially due to needing assumptions to make them more solvable, partially due to the fact that you almost never have all forcing styles in one fluid situation, and partially due to the fact that air has some special features in aerodynamics. So, let's make the three most common assumptions. First, we assume no body forces so that all the terms with A go to zero. This is because gas is light, and generally speaking, gravity acting on the air does not make that big of a difference. Next, we assume the flow is inviscid. In aerodynamics, the forces on objects are mostly dominated by pressure forces. Thus, it is common to see the viscosity set to zero. Last, we will assume the flow is time steady. This means nothing is changing in our observation window over time. We make this last assumption because most of our vehicles are considered to be going at a constant velocity relative to the flow. So, let's mark down our new equations with these assumptions. Here, I'll quickly write out the skeleton of the equations in red and copy and paste them 3 times as I did before. Then in white, I'll mark the variables unique to each equation. In the end, we have 3 shorter equations to work with. The left-hand side represents half of the material derivative, also called the convective acceleration, and the change in momentum due to expansion and compression. The right-hand side is the pressure force. These are called the Euler equations, and they're the most common way to use the conservation of momentum in aerodynamics. Note, if you're familiar with the math notation, you can write these out in vectorized form and use math shortcuts like the nabla. However, I prefer the full differential form expanded out because it hides less of the physics. Now, let's make one last assumption, the incompressible assumption. Maybe our object is moving slow enough that the air is approximately incompressible. Here, incompressibility indicates that rho is constant and it can pop out of derivatives. Also, we know from the conservation of mass that the gradient of the velocity, the sum of the 3 spatial gradients, becomes 0. Now, when this assumption is made, it is also common to say you're considering the flow along a streamline. This can be interpreted as a way of saying you're making the flow one-dimensional, and it follows along the flow path curve instead of one single direction. If you do this and you rearrange some of the terms, you can turn the Euler equations into the famous Bernoulli equation. This equation states that the sum of the pressure and the rho u squared at each point is the same along every point on that streamline. If the flow slows down, the pressure goes up, and vice versa. And finally, we arrive at the conservation of energy equation, the third and final conservation law. This one is rarely used and only generally considered when the flow is compressible or encountering some heating or cooling. The principle here is that, like mass, energy cannot be created or destroyed. However, energy can change form. The general form of the equations for physics is that if there is work applied to a system, or heat is added or leaves the system, the internal energy of the system changes. This is also commonly referred to as the first law in thermodynamics. However, as we have come to understand, when we do it for a fluid, things get super complicated. First, let's take a second and write out the full and general form of the equation. And now, let's consider each term here individually. You might notice that a lot of the terms have the same physical roots as the momentum equation, and that's just because now we are considering the work done by those forces instead of the forces themselves. The first set of terms is the traditional and convective changes of a peculiar term, rho times E plus U squared over 2. This term represents the two forms of the energy of the fluid, the internal energy and the block flow kinetic energy. Second, we have this compression expansion term again, which represents how energy leaves or enters the system as stuff expands out or compresses in. And that's it for the left-hand side. Now, the right-hand side represents all the things that can change the flow's energy. The first right-hand side term is the heat in or out of the system. Maybe there's an external heating source, or the temperature outside of the observation window is cooler. This represents the radiative transfer of heat. Second, we had a pressure force, so now we also consider the work done by that pressure. Each term represents the pressure work in each direction. Third, we have the work done by the body force, and similarly, each term represents the work by the body force in each direction. And last, we have the two cop-out terms where we just make new symbols that represent the work done by viscosity and the heat added due to viscosity. Viscosity has the special ability to take the flow kinetic energy and turn it into heat. This is called viscous dissipation, and it's the reason it gets this special term. And that's it. Like the momentum equation, you rarely see the energy equation in its full form. Let's apply common assumptions for aerodynamics. First, we assume the flow is steady. Second, we assume it is inviscid. Third, we assume it's adiabatic, which is a specific assumption for the energy equation that indicates no heat is added or lost in the system. And fourth, we assume the flow has no body force. Let's write out the equation with our new assumptions. This slightly more approachable energy equation applies to steady, inviscid, adiabatic systems with no influence of a body force, and will get the most attention in aerodynamics. You might notice with our third equation that we've added the variable E, which means we need another equation to solve for it. Commonly, we apply the thermodynamic state relation for E that says it must be a function of the temperature and the specific heat. However, adding this equation adds yet another variable, T, temperature, which we need the ideal gas law to solve for. So, we have 5 total equations, the 3 conservation laws and these last 2, and 5 variables to solve for: velocity, pressure, density, energy, and temperature. Easy, right? Nope, not even a little bit. Theoretically, these 5 equations fully describe every fluid flow ever, from the blood flowing through our bodies to the ocean and atmospheric flows on our planet. However, they're not even remotely solvable in their full form, at least not with current technology. In practice, we use simplified versions of these equations that work for very specific flow situations. And even then, with all of our fancy assumptions, it still might not work. Consider 3 examples. Maybe you have a simple fluid flow through a contraction. Nothing too fast, and most of the flow is far from a boundary that would cause viscosity issue. Here, you would use the conservation of momentum with enough assumptions that it becomes the Bernoulli equation, and you just relate the velocity and pressure from one end to the other. This is a common method for measuring the velocity of a wind tunnel contraction. Now, maybe you're studying a commercial aircraft airfoil flow. Generally, the flow is subsonic, but it isn't impossible for parts of the flow to reach transonic or supersonic speeds, and you might see small shock waves. So, you might be able to use the inviscid, steady, no body force form of the conservation equations and turn these into the Mach equations, which we'll learn about later in the course. And lastly, maybe somehow you find yourself going Mach 5 or above. This region is hypersonic and is just a mess. The shock wave is super compressed against the surface and there's just a ton of heat. Here, the properties of a gas break down and the molecules start breaking apart. So, most of our conservation laws don't work anymore. These situations get a lot more difficult to approach theoretically. and likely need supplement from empirical observations. And that's it. Let's review what we've done today. We started by introducing our conservation laws, the sets of rules our fluid must follow to obey physics. We set out to approach each equation physically, starting with the conservation of mass. Here, the difference between mass in and out represents the change in mass. Next, we wrote out the conservation of momentum equation, or the Navier-Stokes equations, the fluid form of F equals ma. With some assumptions, this could simplify down to the Euler equations or even the Bernoulli equation. Last, we considered the energy equation, which introduced two new variables, the internal energy and the fluid temperature, that both required more equations to solve for. And we concluded on a practical note of how we might see these equations and use them in real life. Thanks for watching, and I'll see you next time.